Hello students, today we will be solving some numericals on population growth. Let us begin with our first problem. The problem reads like this. If a population of 50 paramecium present in a pool increased to 150 after an hour, what would be the absolute growth rate of population? If a population of 50 parameciums present in a pool increases to 150, parameciums after an hour, what would be the absolute growth rate of population? Now, in order to solve this question, we need to first understand what is absolute growth. Absolute growth is growth per unit time. Now, the question is how to find out growth. Growth can be found out like this. We know initial population N0 is 50 parameciums. Final population NT is 150 parameciums. So delta N or change or growth in population is NT minus N0, which is 150 minus 50. Therefore, growth or change in population is 100 paramecium. Now, what is the unit time? The unit time here is 1 hour. Now, let us substitute these two in the above equation. So we get 100 parameciums per hour. Now for the same previous problem where 50 parameciums multiplied and became 150 in 1 hour, let us calculate what is the percent growth. Now from previous problem we know growth per individual is 2. And percent growth can be written as 100 into growth per individual. Now basically we have to find out if each individual is producing 2 parameciums, then 100 individuals would produce how many parameciums? That is what is percent growth. So it would be 100 into 2, which is 200%. So that means in every hour, the population is going to become double. Let us move to next problem. A protozoan reproduces by binary fission. What will be the number of protozoans in its population after 6 generations? Now this is a problem on binary fission. Now similar problems on mitosis can also be solved using this equation 2 to the power of n, where n is number of rounds of binary fission or mitosis. This 2n will give you number of offsprings at the end of mitosis or binary fission. Please remember, this formula can't be applied to meiosis and multiple fissions. Right, so it is given number of generations are 6. So at the end of 6 generations, one would have 2 to the power of 6 protozoans, which is 64 protozoans. Next problem. In 2005, for each of 14 million people present in a country, zero point 0.028 individuals were born and 0.008 died. During the same year. Using exponential equation, predict the number of individuals present in 2015. Now let us see what all data is given here. So initial population N0 is 14 million. Birth rate is 0.028. Death rate is 008. Population after 10 years. In 2005 there are 14 million. We have to calculate what will be the population in 2015. So time duration is 10 years. Now the formula that I would use here is dn by dt equals Rn. Now R we can find out, which is B minus D, and it is 0.02. So change in population per year is given by the above formula dn by dt, which will be 0.02 into 14. So this gives us a value of 0.28 million per year. So that means 0.28 million individuals are getting added to this population every year. But we have to find out population at the end of 10 years. So we would multiply this by 10 with 10. So increase in population after 10 years would be 0.28 into 10, which is 2.8 million. Now population at the end of 10 years would be this increase in population added to this initial population, which is 14 million. So population at the end of 2015 would be 14 million plus 2.8 million, which would be 16.8 million individuals. Moving to next question. In a pond there were 400 frogs last year. Frogs were added to take the current population to 600. Calculate the birth rate. Now change in population delta n is clearly given as 200 frogs. Time duration is 1 year. Now birth rate is defined as delta n by n naught into t, where n naught, which is initial population, is 400 frogs. So let us substitute all these values in the equation. 200 by 400 into 1, which which would be 0.5 frogs per year. Let us take another problem. The problem reads like this. In a population of 2,500, whose intrinsic rate of natural increase, which is R, is 0.2 per capital per year, is exhibiting exponential growth. If the number of individuals at a given moment is 2000, calculate the population size after 1 year. Now there is one very important thing to notice here, and it is this value of 2,500. Now this value has no significance to the problem that we are dealing with. Now what are the values that we must consider are? First is the initial population, which is at this given moment, which is 2000. So N naught is 2000. Also consider the R value. R is 0.2. And not to forget what type of growth it is showing. Exponential growth. So we have to calculate the population size after 1 year, where T is 1. Now these are all the given values. Now my approach would be, I would take the formula dN by dt equals Rn, and first find out what is the change in population after 1 year. So that would be, since R is given as 0.2 and N is known as 2000, it will be 400 individuals which are added to the population at the end of 1 year. Now the population after 1 year would be this change in population plus the initial population of 2000. So population at the end of 1 year is initial population plus change in population. Now initial population N naught is 2000 plus 400, which would be 2400 individuals at the end of the year. In a population of a habitat in 1 year, sorry, 200 births, 150 deaths, 200 immigrations, and 150 immigrations have occurred. The density of the population will be what is the nature of change seen in the population. That is, whether it increased, decreased, remained same, or it is not possible to predict. Which one of these would be observed? The formula which will help us solve these type of questions will be nt plus 1 equals nt b plus I minus d plus e, where B is the number of births, I is immigration, D is number of deaths, and E is number of immigrations. So this is how we can find out the influence of all these factors: birth, death, immigration and immigration on the population. So substituting the values in this equation, (200 plus 150 minus 150 plus 200. This would be NT 350 minus 350, which makes NT plus 1, population at the end of the given duration, same as the initial population, which is NT. So we can say in the population. That is, it has neither increased nor decreased. It has remained same. The next problem is how to find out R value when B and D are given. The problem is like this. In a population, per capita birth rate is 0.15. And per capita death rate is 0.08. What is the value of R? Now we have to use the formula R equals B minus D. So this would be 0.15 minus 0.08, which should be 0.07. Next problem. In a population, there are 600 individuals at the beginning of the year. During the same year, '84 individuals died, and 54 new individuals are born. The birth and death rates for the population will be now the formula that we have to use here is birth rate is B by NT and death rate is D by NT, where B is number of births, D is number of deaths, N is initial population, and T is time period. Now let us substitute this and find out the birth rate first. So birth rate will be 54 by initial population 600 per year. Time period is 1 year. And death rate will be 84 by 600 into 1. So this will give us a value of 0.09. So birth rate is 0.09 and death rate is 0.14. The next problem is like this. The number of births and deaths of 4 populations A, B, C and D are as given below. The question is, which population has highest birth rate? Now growth rate is given by the formula B minus D by NT, where B is number of births, D is number of deaths, N is the initial population, and T is time period. Since time period is not mentioned here, we would consider it as a unit time period and take it as 1. Now substituting the values for populations A, B, C and D, the above equation, we get following growth rates for population A, B, C and D. So the population with highest growth rate is population A, whose growth rate is 0.1.